I'm going to ask and answer a bunch of questions about how your signal works around your display, and we'll look at things about, you know, why do things flicker, how far can you drive things, what do things like null pixels and everything do. So I want to talk about, you know, wiring and how it affects voltage. I want to look at what the actual 2811 signal looks like. So you begin to understand how these pixels actually work, what sort of degradation you get over different types of wiring, so you get a feeling for how the types of wiring choices that you might make will make a difference to your display. I want to look at 5 volts and 12 volt pixels and maybe answer the questions, is Mo volts really Mo better, or is it actually or worse, and or are there situations where it's better and situations where it's worse? I do want to look at things like, you know, F amps and null pixels and what happens and what sorts of problems they do actually solve for. Want to look at comparing the differential signals. So what does a DMX signal look like? What does a differential signal look like that comes from a controller? And what are some of the things that you need to consider there? And look at terminating resistors and the like. And then, yeah, we'll look at some things around interference and the like. So let's get into it. So to prepare for this presentation, this kind of goes on from last year. Last year at the Sydney Mini, I brought along a bunch of wire and we hooked a bunch of things up, and we hooked up the oscilloscope and we looked at some signals, and, you know, it was interesting. I had fun with it, and I think the folks that were in the session seemed to sort of learn something from it. But there was definitely some things that when I came away from that session, I thought, you know what, I actually really don't understand why that behaved that way. So for instance, why, if you put a F amp immediately after a Falcon controller, does it suddenly seem to be better? Why isn't it that you have to put it further down the wire, which is what I'd always believed in the past? And so try to work out the answers to those questions. And so I've done a bunch of additional testing here with more wire, more controller types, and I'm going to sort of run through it with you today, and hopefully you'll walk away from it. I tested with a bunch of different types of wire. Each piece of wire was 20 meters long, about 66 feet. So a long piece of wire. And most of my tests are focused on the distance between the controller and the first pixel. I'll talk a little bit about what happens after that, but that first travel is the most important part, because once it gets to the first pixel, most of the signal gets refreshed. Now, that's not a perfect situation. You'll still get flicker for various other reasons, but that first run makes a huge difference. Then we're gonna test it with a bunch of different types of wire. So one type of wire is alarm wire. This stuff is incredibly small. This is 4 cores. You can see how small it is. That wire is no thicker than the head of, this is a AA battery. It's 26 AWG, or 0.14 millimeters squared. It's tiny. Where I have 4 wires, I always connect 2 grounds together, and you'll see why that's actually a really, really good idea. Where it's paired, you would always also use one from each pair for the ground as well, rather than running the grounds on the same pair and then the data and the positive on the other. I also ran it across Cat5e. This was solid Cat5 cable. So I ran a test with that. There's data cable. This is well, it's actually a 5 core. There is this extra thing which I don't generally use. It's also got some shielding on it. It's got 2 white wires, which I typically use for the ground. And then it's got an orange and a blue, and you run data and power across those. They're a little bit bigger at 0.22 square millimeters. This is also a stranded wire. It's not a solid wire. Then use speaker wire. This is like a 2-core wire. So if you want to run 3, you need to run an extra piece of it. So it's a bit of a mess to run. But again, it's a slightly higher gauge. I use this a lot for my power injection in my display. It's relatively cheap. And, you know, comes in 100-meter rolls, but you can also run data across it as well, and that we'll do that here. And then finally, this is the light extension cords you get from Bunnings. You know, you get 20 meters for, I don't know, $15 or something. So it's, you know, 17 AWG, 1 millimeter squared stranded wire, And so we'll use that in the tests as well. So first of all, let's talk about voltage drop. All wire has resistance. It's not a huge amount of resistance, but it's some. Also, you need to understand that the resistance varies by the current draw. And so you need to be careful that when you're looking at voltage drop, you don't just apply the voltage at the controller, go to the end of the wire and measure the voltage to see what the voltage drop is, because it generally will be next to none because there's almost no current being drawn through the wire. But as you start to turn pixels on, and the more pixels you turn on, the more current that goes through it. And so the voltage drop will start to increase. So you have to be careful how you test voltage. If you ever want to go and test to see what the voltage is on your pixels, turn the pixels on and then check the voltage. Don't check the voltage without the pixels being on. Because V equals I times R might be a really small number, but if I is 0, then this is always going to be a 0 voltage drop. So to test properly, you have to add load. So most of my tests, I have a picture like this to talk about it, but in this test here, what I've done is I've got my controller, I've got my test piece of wire, I've got a test point, and then I've got a bunch of pixels here to represent the load. Where I've done the 5-volt tests, it's typically 38 pixels at 100% white, and where I've done 12 volts, I'm using those 3 LED nodes, so there's 20 of those times 3 LEDs, so a total of 60 actual LEDs, and again, I'm running them at 100% white to put a load on the wire. Now, both of these are a pretty light load. But, you know, the idea here is not to test all the variations. The idea here is to see what are the differences the wires are making and therefore try to limit the variability. So let's look at our voltage drop. So the resistance here has been calculated just by basically putting a multimeter over the cable. And you can see, as you would expect, as the wire diameter goes up, the effective resistance of the wire is much lower. The other thing to remember is the wire effectively runs in both directions. So the power comes out from the controller to your pixel, but then the ground returns back to the controller. So you can effectively double the resistance because it'll affect both sides. And this is something that I think John Spike has talked about in the past, about how the ground actually moves. It's not just the voltage that drops. The ground lifts and the voltage drops, and it's the difference between the two that you measure on the end, but it's not the whole story, and you'll see why that's a big deal. So when I run these, and when I run them at 5 volts with my 38 LEDs over each one of these cables, you can see that the really thin wire, you start to run into problems. You get color fading. This also hints at one of the big differences between 5-volt pixels and 12-volt pixels. 5-volt pixels, from a signal integrity sense, are incredibly stable. It is almost, in fact, I've never managed to get glitching on 5-volt pixels. They will pretty much always work until they just don't work. And we'll explain why that is a little bit later. But what you will get, of course, is color problems, and the color, as the voltage drops, starts to drop away until you lose the blue LED first, then you lose the green, and then finally you lose the red. 12-volt pixels are different. 12-volt pixels, you will almost never get this color fading. You will, but you have to go a lot harder, a lot further before that happens. But what you will get is you will get signal glitching problems where the pixels glitch. And depending on the sorts of data you're sending, depends on whether it'll either glitch, it'll either flash on and off, or it'll glitch different colors, or in some cases it will lock on to white and just stay white all the time. And I've definitely seen that in my display, and never fully understood what was going on, but I do now. But you're much more likely to get this with 12-volt pixels than you are with 5-volt pixels. So what does a WS2811 signal look like? Well, you can go and have a look at the data sheet. And if you're into reading data sheets, it lays it all out. But effectively, the 2811 is a chip, and it always runs at 5 volts. Even when you've got 12-volt pixels, the 2811 chip is still a 5-volt chip. It's very low current. It hardly pulls any at all, right? So it's definitely not a factor in the voltage drop. It receives a signal at 800 kilohertz. Okay, so this speed here is constant. They can run at half this rate, but all of ours are running at 800 kilohertz. And this is what limits the number of pixels that can be updated in a given period of time, is this 800 kilohertz frequency. The signal's a square wave, as I show here. And this rise at the beginning here is the critical factor. This rise has to rise to at least 0.7 of the voltage. So if there's 5 volts being provided to the chip, then this voltage has to rise to at least 3.5 volts in order for the chip to trigger and think that it's going to get a signal. If it never reaches 3.5 volts, the 2811 chip will just sit there and not receive any signal, even though your controller is trying to drive it. And a number of the failure scenarios we'll see today are as a result of it not getting to that threshold voltage. Now, the interesting thing here is that this is expressed in terms of this voltage. So if you're not actually powering the chip to 5 volts, let's say the voltage that you're actually delivering to the chip is only 4 volts, then the rising edge only has to rise to 0.7 times 4 volts, which is obviously lower. You can do the math. It's what, 2.8 volts. And so this only has to rise to 2.8 volts to trigger the signal to be read. And this in part explains why 5-volt pixels generally work really well and don't glitch. Because when 5-volt pixels are run in long runs, the voltage provided to the chip also drops as much as everything else drops. And so this threshold voltage keeps dropping as well. And so even though the voltages are quite low, the chip is still able to read the signal. Whereas with 12-volt pixels do a much better job of delivering the full 5 volts to the chip. But because the signal voltage doesn't necessarily starts to fall away, and we'll see that, you can run into problems where this rising edge at the beginning doesn't actually rise enough, and so the chip stops reading it. And when the chip stops reading it, that's when your glitching starts to happen. Now, the signals are a different shape if it's a 0 or a 1. Effectively, what it is it's a rise in both signals, but then it stays high for a shorter period of time if it's a 0, and then it drops back down to 0 again. When it's a 1, it rises and then it holds higher for longer. And effectively what the chip does is when it detects this rising edge, it waits a given period of time and then it samples the signal. And if the signal happens to be low, then it's reading a 0. And if the signal happens to be high, then it's reading a 1. And all your controller is varying the shape or the length of this rise in order to send 0s and 1s out to your pixels. Now, how when you're sending the data to the pixels, does it know to start back at the beginning again? Well, the answer is it drops to 0 and it holds at 0 for 50 microseconds. And if it gets a 0 for 50 microseconds, at that point, the first pixel says, okay, the next piece of data is now for me. And so that's the reset. So if 1 bit takes 1.25 microseconds, then you can get about 800,000 bits per second along the wire. 3 bytes, which of course would be the data consumed by a pixel, takes 30 microseconds, which means you get 33,333 pixels a second, but that's without a reset. But if you want to do 20 frames a second, you can effectively drive up to 1,665 pixels. Right, that is the maximum rate at 20 frames a second. If you're at 40 frames a second, then the maximum theoretical number of pixels you could drive is 831. Now, as I said in my earlier presentation, none of the pixel controllers out there will run at this rate. And the reason is because they need some of this time to prepare the data for the next frame. And so depending on the power or capability of a controller depends on how much of this time they need to steal. And so the FPP controllers can typically achieve about 1400. The Falcon will achieve about 1024. And some of the older controllers might only be able to achieve 340 because they need to steal so much more time to prepare the data. So that's why not all controllers can run actually that many pixels. It's impossible to update it any faster than this. These are the maximums. All right, so that's why you can't get 5,000 pixels on a run and achieve 20 frames a second. It's just not possible. All right. So there's two ways to look at signals. One way is with a digital signal analyzer, and this is a tool that most of your controller vendors would have used when they were developing it, and allows you to see the signal on the wire. So this is not a hypothetical signal. This is actually the signal that has been measured from a controller, and you can see the actual timings that this controller is delivering. Here you can see a 1. Here you can see a 0. All right, and the frequency is 800 kilohertz, which is what you'd expect it to be. What you're also seeing here, this is a slightly different time scale, and so what you're seeing here is a block of data being sent. So this is actually a bunch of ups and downs, and then you see this long quiet period. Well, this is the quiet period between frames. Now, it's a lot longer than it needs to be, but there was only a handful of pixels on this thing, which is why so much of this time is quiet. So what does it really look like? Well, this is an oscilloscope sample. This one is taken immediately after the 38th pixel in my 5-volt pixels. It's a little wavy down here. That's some AC coupling that's come from the way I had it configured. But here you see a 0 and here you see a 1. What you'll also notice is that the waveform is nowhere near as nice as it was here. Right, and the reason is this is how the computer sees it, right? This is what the voltage actually looks like on the wire. And so you get a few artifacts here. So first of all, you'll notice that the rises aren't perfect. You know, there's some rounding here. It sort of rises over a little bit of time, and the fall also takes a little bit of time, right? And that's just an artifact of capacitance in the wire and also resonance. We'll talk a little bit more about those as well. So here's it zooming in onto a single waveform, and you can see this rise time problem, and you can see this fall time problem as well. And this rise time issue occurs because the wire is effectively a capacitor. There is some capacitance between the data wire and the ground wire, and so you see this slowness in the rise time. The fall time is actually, it's slightly different. Let's not worry so much about that. So when a 2811 chip is going to read this signal, remember we said that if the voltage was provided was 5 volts, then it was going to trigger at 3.5 volts. Well, 3.5 volts is actually at this point here, right? And so this is actually when the 2811 chip will see the signal start. Not here and not here, but here, okay? And where it'll see it fall is actually here, because that's the trigger voltage at which it considers the thing to be off. And so that square wave that you saw from the digital signal analyzer is actually starting here and ending here, and not actually reflective of the shape of the signal. Now, why is this a big deal? Well, this is a big deal because the signals are not as clean as this, particularly not after you've got a long piece of wire. So let's look at what happens if you set this thing up just as we had before, but instead of just testing the voltage here, let's put the oscilloscope on here and see what our signals look like. And that's what they actually look like. And that's pretty damn ugly. These here are all zeros. This is a 0. This is a 1. You'll notice the 0 here doesn't get as high. The 1 here, it's got this foot on the end of it, right? It's really, really messy. This is using the power cable, so the wire that had the least resistance. So there's the least amount of voltage drop across the wire, but there's lots of signal deformity going on here. And depending on how bad this signal deformity gets, depends on how bad it's going to be. So take the 0 here. The 0 here is triggering at this point here, assuming that this chip is getting 5 volts. Of course, it's a 5-volt pixel, so it's probably not getting 5 volts. So it's probably actually triggering a bit earlier. But if it was getting 5 volts, it's not going to actually see the rising edge until this point here. Now, That's not actually going to be a problem, because if you remember from our 2811 signal, when it sees the rising edge, it's just going to wait a period of time and it's going to sample it, and it's still going to be low at that point. So it's still going to read it as a 0, but it's awfully close to not reading it at all. The one here on the 12 volts, and this is much more likely to be accurate, you can see that it's wider, but it's a long way away from when the signal actually started to rise before it actually detects the rising edge. And if this had been much later, this 1 would probably have been read as a 0, right? And of course, that can lead to flickering. Speaker wire. Speaker wire here produces the best of all possible results. And that may be in part because the way in which the speaker wire had to be set up, because the speaker wire was not 3-core, it was 2-core. I had the ground and the signal going over one pair, and then I had the positive wire and a separate wire that was kind of cable tied every 50 centimeters or so along the wire. And so there is nowhere near as much interference in this signal. It's actually a lot better. So it reads a lot cleaner. This is the Cat 5e. Similar problems, a little bit better maybe. Definitely seems to read the 0 and 1 a bit better. This is our data cable. So our data cable was that thin multi-stranded wire. This one's a bit scary. And our alarm wire actually gets awfully close to not reading it at all. And even worse down here on the 12 volts. This is really concerning. And that's why, sorry, and that's why this flickers, right? Because quite frankly, this here is not really enough. And so it's quite possible that this is being missed. And so it's being read as 0s and it's starting to flicker and go crazy. So why is it this shape? Well, the first thing is capacitance, right? So wherever you have 2 parallel wires, where one's positive and one's negative, there is a charge that is built up between the wires, which is called capacitance. And what that means is when you apply a sudden change in voltage on these wires, instead of them changing suddenly at the other end, they change more slowly because the capacitance builds up, or the charge gets absorbed by the space between the wires. And so the signal at the other end has that distinctive rounded shape as it comes up. Okay, so it slows the rise, and it also slows the fall, right? And one of the reasons why it slows the fall is because when the voltage falls suddenly, that charge that existed between the wires starts to get returned back into the wire, and so you get this sort of slowing down as well. So capacitance is a big factor, but not the only factor. Longer the wire, the more capacitance is always true. So 12 volt flickering over a power wire, right? Despite running 12 volt, these pixels flickers over the best wire. So I was running the best wire here and it still flickers. And one of the things that you'll notice here is you get some real significant differences here. When the signals are 0, it goes from 0.6 volts to 3.28 volts, which is only 3.12 volts peak to peak. And remember from our very first slide, with a 12 volt pixel, it's probably providing 5 volts to the chip. And so it needs 3.5 volts to read the signal. So this is not going to read the signal. However, when the signals are 1, it goes from 0.8 volts to 4.6 volts, which is 3.76 volts, which it is going to read as a 1. Right, so this is firmly in unreliable signal territory, and so you're going to get flickering on these 12 volt pixels that you won't get on your 5 volt pixels. This is the money slide. If you can walk away from this presentation understanding this slide, you'll really begin to understand why pixels flicker. So here, what I'm doing, and I'm going to talk you through it, right? So we're running 12 volt pixels here. So this is, at this point here, I'm measuring the voltage on the controller. So the ground is truly 0 volts. The data signal is coming out is about 5 volts. The actual controller voltage is 11.51 or thereabouts within an error factor. So it's not quite 12 volts, but it's close to. If I then go to the end of the wire and I turn the pixels on a really dim red, just bright enough so that I can see them, we're starting to draw some current through the wire. And we see a couple of things happen. We do see that the ground is no longer zero, right? Because of the resistance in the wire causes this voltage to change from the zero, and it's now slightly above zero. The data voltage has dropped a little bit, not significantly, and the 12 volts has dropped well, it's actually increased, but in reality, it's dropped a little bit. But it's basically not much has changed here. Everything's good. However, when I turn the pixels on, so I'm still measuring it at the end of the wire here, but now I've turned all of those pixels on full white. And the big difference you'll notice here is that the ground has moved up quite significantly and the positives dropped. Okay, and if I was to measure the voltage at the end of the wire at this point in time, it would be 10.9 volts minus 1.28 volts, okay, which is going to be 9-ish volts, right? But there's an important thing here, right? That's kind of by the by. This is heaps of voltage. But have a look at the gap between the data wire and the ground voltage. This is a problem. This is now only, what, 3.6, 3.4, less than that, right? 3.32 volts between the positive and the negative voltage, right? But we need 3.5 volts to read the signal. This voltage here is not enough to actually trigger the 2811 chip. And so you'll notice it's got nothing to do with the positive wire. It's got everything to do with this ground wire. And this is why one of the ways in which you can fix this is to add more ground wire. You don't need to add any more positive. The positive's fine. But if you added another ground wire, let's say you duplicated your ground wire, that would halve the resistance here. So instead of 1.28 volts, you'd be something around 0.64 volts, which again would create enough separation. Now remember here, we're just worried about the travel to the first pixel, because once it comes out of the first pixel, things change. So what does an F-amp do at this point? Well, what an F-amp does is two things, and you'll see this in a few pictures in a second. But what it does is it re-references the signal voltage. So what it will do is the ground wire will stay the same, but it will boost this signal voltage up to 6.29 volts relative to the original controller ground. But most significantly, it'll keep it 5 volts away from the effective ground that the pixel is seeing, and that makes the signal stronger. Right? So that's why throwing an F-amp into the wire or a null buffer, one of the Hansen null buffers, etc., that's why it helps the signal. It's got nothing to do with the positive line. It's all got to do with the ground wire and the data signal and increasing the separation, because the reason the 12-volt pixels flicker is that the ground lifts and gets too close to the data wire voltage, and the separation between these two becomes too low for the 2811 chip to actually read the signal correctly. Does that make sense before I move on?
Very much, Keith. That's excellent.
Yeah. Question.
Yeah.
Do you know how the F-amp determines what the original voltage was?
It doesn't. It doesn't care. What it's doing is, what happens in the F-amp is the F-amp receives this 10.9 versus, well, it's not 10.9, it's 9 point whatever it is.
Yep.
Right. And it reads the signal. Now, the thing about the F-amp is the F-amp reads the signal differently to the way that the pixel does. It uses a much lower threshold for turn on.
Okay.
Right. And when it produces the output, it produces the output at 5 volts above whatever the ground is at that point.
Yep. Yep.
So as long as this voltage here is above 5 volts, this will be 5 volts.
Yep. That makes sense.
Okay. All right. So there are two ways that the 2811 chip can misinterpret the signal, right? If the ones are effectively shortened, then the chip will see the signal, but it'll see the leading edge so late that it'll read it as a 0 when it should have been a 1. And so that's a common cause, and I had this a number of times in my testing, where my pixels would go white for one frame and then black for the next one. And the reason is when the pixels were off, all the voltages were good because there was no current being drawn. And so the signal would go down the wire, it would see it, it would read it as a 1, and it would turn all the pixels on. As soon as it turned all the pixels on, there was this massive current draw down the wire. And when the next signal came down for the next frame, all of the signals were degraded, and now all of those 1s were being read as 0s. So it would turn all the pixels off. And then the next frame, they'd all be off, so there'd be no current draw. So it would read the next frame as a 1. And so the pixels would flash on and off. Now, that works kind of well where you're sending out a fully on white color. But if I was sending other colors, what I would have seen is various color flickering, because the signal would have been read all over the place. And the back end of my string would have probably locked on white, and the front end of my string would have flickered all sorts of colors. The other thing can happen is the zeros never get to the threshold voltage, so the entire signal is missed. And depending on how bad this gets, this can lead to a string of pixels actually locking on white. And I used to get this in my show. I have some 12-volt pixels for my icicles. And when I was running my test at the beginning, I would run my test at 100%, and it would go red, green, blue, white, and then it would just lock on white. And the reason is when it hit the white signal was red, all the pixels went on white. But after that point, none of the threshold voltages would be hit. And so my pixels never thought they never got another signal, and so they just stayed white forever. And the only way to reset them was to turn the power off and turn the power back on again. So that's the sort of things that you get. All right. So this was an interesting exercise. Most people have never noticed it, but on the Falcon and the SAN devices as well, and possibly some others, there's actually these resistor networks that sit behind the greenies. And these resistor networks are basically the data signal passes through 2 of these wires on its way out. And depending on what this resistance is, depends on how much signal reflection you get. And the sign of signal reflection is this sort of foot that you get at the end of the signal. You see when it drops away, it doesn't quite drop to 0. It goes through this sort of little step. Well, that's a sign of impedance mismatch in the wire. And one of the problems is if you don't get this resistance value right, the signal will degrade. So I took my Falcon, I took my resistor network out, and I started to replace the resistor network with different values. Now, by default, the Falcon has a 100 ohm resistor network that's sitting behind there. But you'll notice that once you get down to 30 ohm or 50 ohm, you actually get a much, much better signal shape. And this is really interesting, and I don't know why this came about, but you actually, by specification, should have a 33 ohm resistor here rather than 100 ohms, and that would give you a signal shape that is much more like this. It would possibly provide slightly little less protection, but it would provide much better driving power down the wire. And interestingly, this is exactly what the F-amp does. One of the reasons why putting an F-amp immediately after your Falcon gets you better distance is because the F-amp has a 30 ohm resistor in it and not 100 ohms. And so you get a signal that looks like this rather than a signal that looks like this. All right, so if you want to get more distance out of your Falcons, pull these out and buy yourself new ones which are 30 ohms or 33 ohms and replace them, and you'll get a signal that looks more like this, and you'll get better distance out of your Falcon. These things are 57 cents a piece from Element 14 or the other part supplier here. It's actually interesting because some of the other tests that I've done a little bit later here on various different types of controllers, this is the biggest factor in the performance of a controller in driving to the first pixel by far. And there's only one controller that gets it absolutely right. So how does the type and voltage of pixels impact the signal? Well, I put this spreadsheet together for you, which will actually work it all out. But yeah, it's complicated. It's really complicated. And even this is a model, right? So it's not a perfect situation. So maybe what we should do is just boil it down into some simple rules. Right, so let's start with 5-volt pixels. 5-volt pixels, your signal reception is pretty much always okay. Putting an F amp on a 5-volt pixel is, generally speaking, a waste of money unless you're just trying to solve for that resistance problem, and you would be better off spending your 57 cents and getting your resistor network. There is the signal detection by the chip is generally really good because of the 5-volt. The 5 volts going down the wire is generally pretty degraded, and the chip degrades at the same point, and so detection's really good. Your main problem is one of color loss, and of course you solve that with power injection, as anyone who uses 5 volts would be doing. There's two types of 12-volt pixels, and interestingly, they demonstrate different behaviors, and those behaviors are really easy to explain. So 12-volt resistive pixels, so these are the older style pixels where they use a resistor to drop the voltage down to 5 volts to drive the 2811 chip. Generally speaking, you will get obviously longer runs without color loss with 12-volt pixels, and that's universally true with 12-volt pixels. Because you've got the 12 volts, you can run it a lot further before the voltage falls to a point where the pixels start to lose colors. But 12-volt resistive pixels will lose color before the regulated pixels. You won't get to drive them quite as far as a regulated pixel. If you push them hard enough, you will get colors flickering or locked on white, okay? And you can improve this by just throwing in an additional ground wire for the reason that we saw in that previous diagram. You will get better distance to the first pixel with resistive pixels than you will with regulated pixels. And the reason for that is because the resistive pixels basically use a voltage dropper, a resistor, to create the voltage on the 2811 chip, not to the same extent as the 12 volts, but the 12-volt resistive pixels, the voltage on the 2811 chip does actually drop over distance. And as a result of that, the chip does somewhat adjust itself for the drop in voltage and will still read the signal better. Whereas with the 12-volt regulated pixels, because they're using a regulator, the 5 volts that's provided to the 2811 chip is much more consistent. And that means that you're definitely powering everything better, but it means that your signal, your ground lift that you're seeing on those 12-volt pixels is a bigger issue with regulated pixels. So you will get longer runs without color loss than with both of these, but you will get flickering earlier with that long run. Of course, once you get past the first pixel, the 12-volt regulated pixels will be fine, as will the 12-volt resistive pixels. Once you get past the first pixels, you're always going to get more distance out of a 12-volt pixel, but you will always get a longer run with a 5-volt pixel. Right? And I know I run my 5-volt pixels over 20 meters with no problems at all, whereas you get flickering on those 12 volts. Okay, how do you solve this? You can put null pixels in, right? Null pixels will solve this because the null pixel realigns that data signal to the ground at that point. And so even though you've got that resistance over the wire, that null pixel will always refresh the signal. And so you will get distance. So if you're going to use 12-volt pixels, you want to be getting some null buffers because they are going to solve all of your flickering issues. Or you can add more ground wire and try to reduce that voltage lift on the ground wire. Okay, so let's have a look at what these null pixels do. Let's see what they look like. So I'm going to use a 2811 pixel. This is a classic pixel, null pixel. But I also tried the Hansons because I've got some of those and the F amp as well. Here, what I've got is I've got my controller, the buffer. I put the alarm wire in, which was the worst of the wire, and then my test point. So there's my pixel, there's a square node. There's my Hanson null buffer buried inside there somewhere. That's what it actually looks like. And there's the F amp. So here's the null pixel. You can see that the null pixel doesn't really change the waveform significantly. And that's because it's just the same sort of pixel. Whereas the buffers, however, do a much better job. So this is the Hanson null buffer, and you can see it really drives that signal. It gives it a much squarer shape. And you'll also see that it turns on pretty much when the signal starts to rise. It drives it a lot harder, and when it drops it a lot harder as well. So you get a much cleaner signal out of the Hanson buffer. And it's a similar thing with the F-amp. You get a much cleaner signal. This is another one. So here what I've done is I've taken the power wire and I've done a test point just before the buffer and a test point just after the buffer, so you can see what the thing has done. And you can see that it's actually, this is 2 volts a division. So rather than triggering at 3.5 volts or something like that, you can see that it's actually triggering at 2 volts when it drives the signal up. And so this is one of the characteristics of these null buffers, is that they do trigger at a lower voltage, and so they tend to expand the signal back out to its original shape even after it's been degraded, and this is a pretty degraded signal. The other thing is they do tend to turn off a lot earlier. So this turns off as soon as it starts to drop rather than waiting until it's most of the way down. So you do get a much cleaned up signal, and it's a better cleanup of signal than you get with just putting a pixel there. So yeah, these things are really quite neat stuff, and a lot of signaling issues can be solved with them. All right, DMX. So here I'm running DMX over a piece of speaker wire. And the main thing I wanted to highlight here, there's 2 things I wanted to highlight here. So first of all, what is a differential signal? Well, a differential signal is transmitted over 2 different wires. But the interesting thing about a differential signal over the 2 wires is that one of the wires, when it's driven low, the other wire is always driven the opposite way. And so if you look at these 2 signals here, you can see that when this one's low, this one's high. When this one's low, this one's high. And even when there's noise on the wire, there's an equivalent piece of noise on the other side of the wire. And that's what makes this signal incredibly reliable over very long distances. And even if this signal degrades significantly in terms of voltage over a long distance, it's still relatively easy to pull the signal out of the wire. And that's why differential signals are used wherever you need a long distance of transmission. You'll also notice that this signal has these big spikes at the transition from low to high, and from high to low, you get these spikes downwards. The way you solve that is with a terminating 120 ohm resistor. So you may have heard that, you know, if you're using DMX props, you need to, on the last prop in the chain, you need to terminate it with a 120 ohm resistor across the 2 pins. I can't remember which pins it are offhand. What that does is it gets rid of all these signal spikes off the signal and gives you a cleaner signal. Okay, these spikes and reflections, etc., can really muck up the signal. You're not necessarily seeing it here because, to be honest, I was just driving it out across the wire. But if you had lots and lots of props connected to this wire, this would be even worse than it is here. So really problematic. The other thing you'll notice about this signal is that the voltage difference between the low and the high here is 5 volts, and this is 5 volts as well. So there's actually a 10 volt difference between the signals when they're high. So a really significant difference. But when you look at the Falcon differential receivers, you'll see there's a similar problem with termination, and that's why the smart receivers in particular have those terminating resistors, switches on the last board that you need to turn on for similar reasons. But you also see that their voltage movement is less. It's actually only 2.5 volts either way, so it's only a 5 volt signal. So you're not going to get quite as much difference out of a differential receiver than you would potentially out of a DMX, because the voltage is just not there. But yeah, that's what a differential signal looks like. So let's try some different controllers, and see what the signals look like off different controllers and whether they're really all the same. And the answer is they're not. So the F16, in this particular test, I was running 12 volts over the power lead, and I was getting some flickering. And the reason I was getting flickering was because of ones being read at zeros, and so it would flicker off and on. The Culp controller, I got no lights at all. It would not drive the lights over this length of lead. They just stayed off. The Pixelite was perfect. And interestingly, the Sound Devices was perfect, but this is really weird. because it's actually just a bit of a miracle, and it was just a side effect of how I was testing them. The sand devices should have been marginally better than the Colt board, but worse than the Falcon. But in this case, it actually turned out to be reasonably good. And the signal differences that you're seeing here are entirely down to that output resistor that we talked about. That output resistor is the thing that is causing these to be wrong. So the output resistance here is 33 ohms. It's perfect. And it produces a perfect signal, and it drives it perfectly over that distance. The next best is the Falcon, which is 100. The sand devices is 290, and it's actually causing lots of reflection here. And it's actually this reflection that is so bad that it's somehow good. And that's why I say it was just a lucky case. The Colt controllers, as best I can tell, have 1K resistors, which is why the signal strength is really, really poor over distance to the first pixel. This won't make any difference once you get beyond the first pixel. And if you threw an F-amp on the output of the Colt controller, it would work just fine. But yeah, he has way too much resistance on his output data pins to get any distance out of these things. Any questions?
I guess so. Why do they all have different resistor values? Is it because they've never actually measured it, or is there other reasons at play as to why they want to use different resistor values out of the box?
So there is a chance that people were trying to protect the controller, because if a voltage was accidentally applied, then a slightly higher resistance value might slightly protect the controller. In reality, as I understand it, people just didn't read the specs correctly. It's not hidden in the specs, but it's not necessarily obvious in the spec exactly what that resistance value should be. And in fact, many years ago, before I was really heavily involved with actual controllers, there was a storm of controversy around the sand devices, where there was a whole bunch of posts around ripping out these resistor networks and replacing them with different values, because these resistor networks were causing problems and people were replacing them to get better distance. But look, the official pixel, the spec for the 2811 chip says that the optimal value for this resistor is 33 ohms. As you saw in my testing, up to 50, and it's still not too bad. But once you get into 100, if you're trying to drive distance, it can start to cause a problem. Now, if you're not trying to drive distance, this is not such a problem. You put these pixels without the 20-meter lead, the Colt controller would have driven them just fine. It's only because I had that long lead with that ground that was going up and this degradation in the signal that it's a problem. Any other questions?
Yeah, so Will just said in the chat, if you essentially take a Falcon and replace the resistor, you'd have a signal like the Pixelite.
Exactly right. Yes, if you rip it out, which is effectively what I did, right? I replaced that one. I replaced one of the resistors effectively with a different value.
How does that go with other styles of like your 2801s and things like that? Will it have an effect or not really?
So let's let me show you. Let me show you how you would work that out rather than do it. WS2811 data sheet. Let's bring up the data sheet for a 2811 chip. All right, it's a little bit of Chinglish, but so here's the spec here that tells you that it should be a 33 ohm resistor on the input and the output. And you'll notice that it's on the input and the output here. And this is the thing that you're trying to equalize. So because your controller is here driving this thing, you should also have a 33 ohm here. If you bring up the WS2811 data sheet, let's see what it has to say. Does it? So interestingly, unless it's, I mean, it could be buried inside the text somewhere. but yeah, there's not a similar picture. I'd have to read the
fair
whole
enough.
data sheet to work out whether they have actually got a recommendation around the resistance along the data wire. But the 2811 is crystal clear. The value should be 33 ohms. All right. So while I was doing this, I also had some other random questions. And these things, you know, I got a variety of answers to, or non-answers to. What happens if you use shoddy connectors? Something that I like to do. So the only thing about shoddy connectors is that they will obviously introduce additional resistance, which means that voltage lift on your ground wire or the drop on your data wire, etc., will be slightly higher because you're using non-waterproof or waterproof connectors that have degraded. So you do want to keep your connectors reasonably good, particularly if you're trying to get distance out of them, because otherwise the problems that you experience here will be even greater. Do pixels interfere with garage remote controls? So I ran a fair bit of testing on this. Unfortunately, I was just running a single string of pixels at the end of a long piece of wire. I hooked up my software-defined radio, which basically lets me see the electromagnetic spectrum to see if there's any interference going on. And I tested the frequencies that I would have expected to see interference on, which were the frequencies around the 800 to 2400 kilohertz, which is the switching frequency of that signal along that wire. So if that wire was acting as an antenna, I figured, well, maybe I'll be able to see something there. I also went and checked the frequency range, which is common for remote controls. And these, you know, I picked these up off the web, and whether they're the same in Australia as around the world, I assume they are. If they're not, these are frequencies that you know, do at least exist in America. And I went through all of those frequencies. And with that simple setup, I couldn't see any signal that came and went depending on whether I was running my pixels or not. So that doesn't mean, of course, that you can't get interference. It may be that once you add all the pixels, it may be that once you are changing the pixels to different colors and all the PWM is kicking in, etc., it's still possible that there is interference. It just was not possible for me to see it in the ranges that I was looking for. Another thing that I've heard people ask in the past is, should you add a ferrite core to the pixel wire to help the signal? And the answer to that is pretty much no. When you add a ferrite core to a piece of wire, and a ferrite core is that little black bulb that you might see on your power lead or on your USB cable, it's effectively a ferrite, typically a cylinder that the wire is passed around, and it acts as an inductor. And what it does is it filters out high frequency interference. And none of our signals have any of that to filter out. So it's not going to harm the signal, but it's also not going to do anything for the signal either. So I wouldn't be investing in ferrite cores or anything. So my final suggestions, if you're running 5-volt power, inject often, use positive, inject positive and negative. If you're running 12 volts, you may want to consider just adding extra ground wires. If your wiring is such that you have an extra wire, always connect that wire to ground and bolster your ground wire, because it will help your signal distance. Particularly if the positive rail is 9 volts or greater, because you just need more ground. Buffers will definitely help you get more distance, but so would reducing the output resistor on the controller to that 33 ohms or 50 maybe if you want. And if you're using 12 volts, use regulated and add AF amps to address flicker. You will generally, apart from that distance to the first pixel, 12 volt regulated are going to be better than the resistive ones in terms of distance that they deliver and the color that they deliver out the end.
So Keith, the 2801 data sheet says to use a 50 ohm resistor.
Okay, there you go. In
for
which
example.
case, yeah,
And
put a 50 ohm.
Presumably other pixels require other values, which may be why people try and find something in the middle.
So the way the Falcons work is they have this one resistor network, and that resistor network governs two of the outputs, both the clock and the data output. So you're not going to be able to mix them up. You won't be able to have 33 on the data and 50 on the clock. If I were you, I would use the 50, because the 50, in my experimentation, the 50 was good enough